Hello, fsharp. Welcome back. This is going to be an interesting video. I put out a chat and it was not up to the level of quality and in the tone that I want to maintain for this channel. It had a little bit of a clickbaity title. It had a little bit of a hot take feel, and I screwed up. I'm sorry. That is not what I want this channel to feel like. That is not how I want to communicate with you. It's not how I want to present information. I got some really fantastic feedback from people on that video. They left these really wonderful comments on it. And they provided some great insight. And when I read that, I was like, you know what? You're right. I screwed up. And so I delisted the video. I then messaged the people who left comments saying, you know what, I really appreciate you leaving this comment. I am taking the feedback to heart. And I said I would shoot another video where I would present the same information, but in a tone and in the feel of the channel, the heart of the channel. Like when you come here, my intention is for you to learn. My intention is for you to be edified. I want you to grow and be enriched for choosing to spend some time with me. And so I want to honor that. So sincere apologies to anyone who watched that video. I am sorry to those of you who missed it. Fantastic. You got this video. It's going to be the same stuff, just presented in a much better way. And if you saw from the title, I want to discuss the ideas of compilation and interpretation and show how that's kind of a false dichotomy. Like that's not actually a good way of describing how a language is actually executed. And I'm going to end with some surprising things that I believe at the end, as far as, you know, how, like, what are the fastest languages, and compilation interpretation, does it actually matter? So let's dive into, what do we mean by compiling? What does compiling typically mean? And there, even in this definition, it's not as clear as it could be, but generally you have some code and it is getting turned into a different representation. Typically assembly is how we often think about it. And I'm going to leave this very vague, but the important thing is compiling is usually something that happens. It is a moment in time. It is a step, and your source code goes from a code text representation to an assembly representation. And this is something that is closer to the way the machine will actually think when it's actually running. Then there's the idea of interpretation. Oh my goodness. Interpretation. Hopefully I'm spelling that correctly. And the idea is code goes into some processor. I'm going to put it this way. And oh my goodness, my spelling is so off. Some kind of processor, and it is constantly in this like loop of where it's evaluating your code and running it. And so it is working through your code and processing your code and issuing the commands that your code is suggesting. And so the big difference between these is compiling is a thing that happened at a moment in time. An interpretation is something that is taking your code and working through it and processing it and doing the work that the code is intending for you to do. So it doesn't produce a new artifact on the other side. It does the work that you intended to be done with that code. So at the end of the day, it's like, okay, well, I had code and I wanted something done. Typically with assembly, you would then you would send this assembly to the CPU to run. So one compiling produces an artifact, an interpreter or interpretation typically does not produce a new artifact. It is actually just doing the work. Now I want to talk about how F# does it. And hopefully by the end of it, you'll see like, hey, this is actually super murky. Back in the day when we just started with computers, these were very distinct things. And in modern computers and in modern pipelines for how we write code and send it to a CPU to be executed, this becomes very murky. Now, if you're someone who is extremely experienced and you dream in x86, the content of this video is not going to be of interest to you. So please feel free to move on. Don't want to waste your time. If you're a relatively new developer or you haven't spent a bunch of time with thinking about how does my F# actually run, hopefully this will be very informative for you. So typically with F#, we are now in F# world now. You are starting with some file or a collection of files, let's be honest. And it's a collection of F# source files. And when you want to actually like do something with it, like, hey, I want to now turn my F# project, F# solution into something that's actually useful for the client, you then go through this compiling step. And this compiling, so we're going to go through compiling now. And this compiling is being done by the F# compiler. And on the other side of the compiler, it is going to produce a new file, which is typically a .dll or a .exe. And inside of this, what is inside of this file? It is CIL, or a Common Intermediate Language. This is the intermediate language of the .NET runtime. This is clearly a compile step that is happening here. We had an artifact, it went into it got processed, and we produced a new artifact on the other side, compiling. Okay, what happens though when we actually want to run our program? Well, what happens is this .dll or collection of DLLs will go to the CLR. What is the CLR? It is the Common Language Runtime. And the CLR is something, and I've heard it described as like, oh, well, it's like the CLR is like a VM. And it's like, no, it's not a virtual machine. It is your Common Intermediate Language, the CIL. That language is a state machine language, and it is written against the idea of a virtual machine with registers and a stack. But when it comes to actually running it, it's not like your code is actually running in a VM itself. So I think that's something that confused me early on. There is no VM here. The CLR will now take your DLLs, your EXEs, and what it will do is it will do a JIT, or a just-in-time compile. It'll do a JIT compile. So there's another compile step happening here. And what it is doing is it is emitting the assembly for whatever machine you're running on. Now, I'm just going to say x86 all the time, x86 assembly. The same is true for ARM. The same is true for RISC-V. So this translates to all of them. I just typically work in x86. Well, I'm typically targeting x86. And specifically x86_64. So this is the 64-bit extensions to the x86 architecture. So the JIT is taking your code, processing it, and emitting x86 assembly. Okay, that's cool. So this is like the end, right? No, not even close. So from here, what is happening is that this code is now going into the memory. It is into the memory of your computer, right? And from memory, it is going to your CPU. Okay, what's the point there? What are you trying to get at? One moment. Okay, we're back. Sorry, I needed to cue some things up. So inside, it's emitting this x86 assembly. That's going to memory. And then from memory, it's going to your CPU. Well, okay, what's going on here in the, why is it doing that? From here, if we explode this out, we have caches. So we have L3 cache, L2, L1, oh, L1 instruction cache, and L1 data cache. And so it's going to go through all these different cache lines. And we are still thinking an x86 assembly at this point, x86 code. Then it actually reaches the brain, the true nerve center of the CPU. Now let's zoom in on what that is doing. So I am going to bring up the diagram for a Zen 2 processor. So that is what I am currently running. And so once it gets to the L1 cache, then it needs to go through the instruction cache, which is the L1 instruction cache. And then it comes to a decoder. And a decoder is something that actually takes those x86 instructions and turns them into micro-ops. Micro-ops are the true machine code of the CPU. We don't get to see what these things are. You have to work at Intel and AMD or processor designers to actually see what is going on here. Now, why is that important? So back here, we talked about like, hey, we're emitting this x86 assembly. Well, x86 assembly is actually what is called an ISA, or an instruction set architecture. But it is, you could also think of it as the programming language of the CPU. That programming language is actually an abstraction over what is actually going on in the nerve center of the CPU. So you're sending x86 instructions, the programming language of the computer, but when it hits these decode steps and turns them into micro operations, a whole new thing is going on where it says like, okay, I've taken the x86 assembly. I have, and I'm going to make a jump here. I have now turned that, or I would suggest possibly reinterpreted that into the language I speak into. And it has permission to rearrange those micro operations however it sees fit. But at the end of the day, after it goes through all this work, when it comes back out to the cache, when it comes back out to you and is exposed to you again, it will fulfill the contract, which is the x86 instruction set, that language of the CPU. So what all is actually happening in here is kind of hidden from us. We have some insights about, we know there's arithmetic logic units, which are these ALUs. We know there's floating point, gosh, what was the term? Oh my gosh. Oh my gosh, I'm forgetting it. I'm so sorry. But there's these micro operations that are being sent over to ALUs or to the floating point registers. And so everything here is now getting like rearranged. And the CPU has permission to do whatever it wants as long as at the end of the day, it is fulfilling that x86 architecture kind of promises about how Intel and AMD said it would behave. So this, to me, in my opinion, this sounds a lot like what interpretation is, where code is coming in and there is a processor, which is taking that code and actively kind of decoding it and doing whatever instructions you intended for it to do, but it has permission to process it in any way it wants to. At the end of the day, there's not a new artifact that's produced on the other side of this. When an interpreter is running and it's interpreting your code, it isn't producing something new that you're then going to save. It's simply carrying out the actions that you intended, versus a compiler, which is taking your code and then emitting a new artifact. In this case, compiling, often we think of taking source code and generating an assembly. But again, we're not done. What I wanted to show there, though, is that with fsharp, there's compiling that's happening, and also here in the CPU, I would suggest, I often think of this as interpretation. It is interpreting your x86 code and then executing whatever instructions it needs to fulfill the contract of the x86 assembly. We need to come back to the CLR though. So the CLR, we say, is a JIT compiler. It's a just-in-time compiler. At the time you want to run your code, it is taking this common intermediate language and turning it into the assembly of the machine that you are running on. But there's some additional nuances happening here as well. The JIT, the CLR, is a marvel of engineering. And one of the things it does is like, okay, if I want to get the program up and running quickly, I am not going to spend much time looking at this IL, this intermediate language, and turning it into x86. I want to do the fastest translation of IL to x86 possible so that I can get those instructions sent to the CPU and running. Here's the thing though. The CLR has permission to monitor your program and look for hot loops and look for really hot pieces of code. And it can say, you spend a lot of time calling this function or this method. You know what? I, on a separate thread, am actually going to spend some time and try recompiling that and do some more aggressive optimization of it. And we'll probably do another set of videos where I talk about all the different things that a compiler, and specifically a JIT compiler, can do to improve the performance of your code. But suffice to say, it will watch your program, see what is really hot, and say, I need to go spend some more time, see if I can create a better set of x86 instructions that fulfill the IL contract. So we have the CPU is interpreting our x86 and doing its own thing, but it's fulfilling the x86 contract. The CLR is doing the same thing. It has the IL contract. It's like this intermediate language. There are the rules of that language. I am then interpreting it, turning it into x86 assembly, but I give myself permission to go back and reinterpret. And that is one of the things that's really marvelous. And if you're ever doing benchmarking with .NET, that's why you should be using benchmark.net, because one of the things it does when it's running is it's saying like, hey, I'm going to do warm-up runs to make sure that the JIT has actually like run that code hard and identified any hot loops it was going to optimize, and it optimizes them for you. Because the performance of your program will improve over time the longer the CLR has time to like look at your code and see how it behaves and say, like, I need to spend more time optimizing this loop. So one of the things you will often hear, I'll say it this way, I'll go from my point of reference. I often heard that, hey, compiled languages are the fast ones. If you have an interpreted language, it's going to be slow and there's nothing you can do about it. Okay, I get that. I could see that point of view, but in many modern scenarios, and specifically in fsharp, there is this blend of compiling happening and interpreting happening all over the place. At every level, our code is going through these transforms. There is compiling and interpreting going on. I think the only really clean step, and this probably shows my ignorance, my perception is that the only really clean-cut step in here is when the fsharp compiler picks up your source code and generates IL. That happens once. There you go. You have an artifact. So that is a clear-cut compile step. The rest of this chain, though, really looks like a blend of both compiling and, well, I guess recompiling is what you would say the .NET runtime is doing. So it's not interpreting. It is generating x86 assembly, but it gives itself permission to recompile and do hot swaps. It's pretty phenomenal. And then, but with the CPU and the x86, like that really smells like interpretation to me. So that's why when I think about languages, I don't really think of it as, hey, is this a compiled language or is it an interpreted language? I think you could make the argument that really most languages are a blend of all these techniques. And it's really fun and fascinating to look at the lifetime of your code as a whole and see all the different transforms that are happening inside of it. I think one of the most hilarious cases for interpreted languages are not necessarily slow is the K programming language. Now, there is a phenomenal podcast called ArrayCast that is all about array oriented languages or array-based programming languages. And it's really interesting that I love array-oriented languages, array-based programming languages, because they just force you to kind of think in a different way. And what's funny is that one of the absolute fastest languages for processing and analyzing data for Wall Street, for trading, is the K programming language and its ancestors and descendants. It's an interpreted language. Like there's no compiler for K. Like when you want to run K, like you just run it. It's like a script. It's kind of ridiculous. And so I encourage you to kind of open your mind about, hey, is an interpreted language necessarily slow? Is a compiled language necessarily fast? And like, what is a compiled language? What is an interpreted language? It's the beautiful thing is that when it comes to programming languages, there is no like super clear-cut answer. It's actually this whole gamut of colors and different approaches to how we make programming languages run and how we make them run fast. And so for me, this was like a huge kind of aha moment that I had over the last few years as I kept thinking about different programming languages and how they get interpreted into machine code. And it's like, oh, it's not as simple as compile versus interpreted. There's a wide range. And so I really encourage you to go and kind of like explore all the different ways people have been able to take source code and then turn that into computation inside of a CPU. So I hope this was interesting for you. It's kind of been one of the things that I've been exploring and having a real kick. I'm hoping that I'm going to start some kind of CPU deep dive where I just go way deep on how CPUs actually work. I don't really feel qualified to do it yet. I'm going to put a link in the video to a talk by Casey Muratori, who is a great developer. I really appreciate his content. He can be a little possibly abrasive sometimes to some people, but I think if you take everything that he has produced as a whole, you can see that his heart is to be an educator and to help people. And I think that this talk in particular, talking about how CPUs work, is fantastic. And even he admits that he's not a true expert. So, which kind of really intimidates me. But like I said, I love to do a series just on how do CPUs work because I get a real kick out of it. So thank you so much for spending some time with me. It's been a real joy to chat with you. I hope you have a wonderful day. Thank you very much.